Welcome, everybody. So our last interference topic is going to be about single slit interference. And this one is a little bit weird until we really dive into it. And the way that it works is, if we send light through a single opening, we still get interference, even though there's not a second slit open to interfere with it. And the reason for it is something called Huygens principle, which says that if I send light through an opening of any kind, that every single point along that opening can actually be thought of as a new point source of a wave, essentially a very, very narrow, tiny slit. And for a single slit, you're going to have a whole bunch of them kind of stacked up all next. So that is the model that we are going to apply here. You can see I've drawn this picture similar to the one that we've been working with all week. And this time I have a single opening in my mask, which I have given a width A. You'll notice that I gave it a different letter than I used for the distance between slits in double slit interference, just to help us keep things straight. And I've drawn on the screen on the right the pattern that we're going to see. We're going to see if we can try to figure out where this came from. Interestingly, the question that we're going to be able to ask here is a little different than we were able to ask for the double slit case, which is we're only going to be able to ask where are the dark spots on the screen. So that's our question. The way that I'm going to do it is I'm going to zoom in on this single slit and draw some of these triangles that we drew earlier in the week. In particular, what I'm going to notice is if a point at the very top of the slit and a point at the very middle of the slit are canceling out with each other, then it's also going to be true that every other pair of points like this, say this one and this one, are also going to be canceling out. And given that, if every pair of these little slits is canceling out, then all of the light will cancel out and the point on the screen will be dark. So that means that we can set up a little equation using what we know about the destructive interference here. We know from the geometry that the path length difference for destructive interference should be a over 2 times the sine of theta, a over 2 because it's the edge of the slit and the middle of the slit that cancels out. And then that needs to be equal to a half integer, which I've called p here, times the wavelength. And then you'll notice that there's a 2 on both sides of this equation, one on this side, one on this side. So if you want, you can cancel those 2's out and get an equation like a sine theta is equal to p lambda, which will tell you where the dark spots are. And it turns out that this equation will actually work for any integer p, 1, 2, 3, 4, so on. So now we know where the dark spots are going to be for single slit diffraction.